So, welcome to problem solving session for linear algebra. Today we will discuss problems related to syllabus covered in week 5. That is problems related to change of basis, product of vector spaces, quotient spaces, and dual spaces. So we'll start with the first problem related to change of basis. So I hope I'm audible to everyone. Yeah, I guess nobody has said some so far. So I assume that. So let V be R2. So we are in R2 now. And consider the basis of R2, beta is equal to 1, 2, 3, 4, and gamma 7, 3, 4, 2. Okay. And if this matrix A, B, 11 by 2, and this is 19 by 2, and this matrix minus 19 by 2, 11 by 2, C, D, respectively are the matrix of change of basis from beta to gamma and the matrix of change of basis from gamma to beta. What we need to do is find A, B, C, and D. So what they have given is that, so when we have change of basis from beta to gamma, it is equivalent to saying that it is linear transformation matrix of identity map corresponding to beta to gamma. Okay, so what we are given basically is that I from beta to gamma is this 11 by 2, 19 by 2. Yes. And I gamma to beta is minus 19 by 2, 11 by 2, C and D. And what we need to do is we have to find this ABCD. So these are basis chain matrices, and we are to find the corresponding coefficient in this matrix. Then we have to then first, so this A is in first column. So first column corresponding to beta 1, beta 2, and these are corresponding to gamma 1, gamma 2. Okay, so if I am to write this as beta 1, this is beta 2, this is gamma 1 and gamma 2. Then first I have to express beta 1 in terms of gamma 1 and gamma 2. Okay, this is 2. So beta 1 is 1, 2, and I have to write it in terms of gamma 1 and gamma 2. So this is some p times 7, 3 plus q times. So this is my gamma 7342, 4, 2. So what we can do is either you do this, that 1 is equal to, then now p7 plus q4 and 2 will be p3 plus q2, and then you can solve this system of linear equations and then get the values for p and q. Either we can do this, or we are already given that this I beta gamma is a basis change matrix already. So anyway, from this information, I already have that 1, 2 is what? A into 7, 3 plus 11 by 2 into 4, 2, right? So I can directly substitute these values here and I get that this is 1, 2. So we can either solve this system of linear equations and find P and Q. Okay. Or what we can do is, since I beta gamma is this, I get 1, 2. Since I beta gamma is given, what I have is 1, 2 is A 7 comma 3 plus 11 by 4, 11 by 2, 4 comma 2. So what it gives me, that it 1 will be now A7 plus 11 by 2, 4, and 2 is A3 plus 11 by 2 into 2. So this will give me 7A plus 22. And from the first equation itself, I will get 1 is equal to 7A plus 22. And this will give me 7A is equal to 22 minus 22 plus 1, which is minus 21. And then A is equal to minus 3. And will this minus 3 will also solve the second equation, because we are already given that this I beta gamma is basis change matrix. Is it clear? We can either solve the system of equations and then get the values of P and Q, or we can smartly use the given information. That is, given information is I beta gamma is already given and it has this form. So we got that A is minus 3. Similarly, we can do this for the second column. That is, we have to now express beta 2 in terms of gamma 1 and gamma 2. And then what it will be? It is 3 comma 4. Yeah. So we have to, just a second. We have to now express 3 comma 4 is B into 7 comma 3 plus 19 by 2, 4 comma 2 plus 19 by 2, 4 comma 2. And again, we have to solve this linear of equation for B, and we will get 3 is equal to 7B plus 19 by 2, 4, and 4 is equal to again 3B plus 19 by 2, 2. And from here itself, I will get that 3 is equal to 7B plus 38. And this will give me B is equal to minus 15 by, oh, not from this. This is what 4 is equal to 3B plus 19. And this is minus 15 is equal to 3B. And this gives me B is equal to minus 5. Is it okay? Any doubts here? I'm just using the information already given. That second coefficient, when I'm writing beta 2 in terms of gamma 1 and gamma 2, the coefficients are already given here, B and 19 by 2. So second second scalar or scalar multiple of second element in the linear combination of beta 2 in terms of gamma 1 and gamma 2 is 19 by 2 is already given. So we are using that fact. And then we got that A is minus 3 and B is minus 5. And now we have to find the C and D. So now note that C and D is now in the second column of this I gamma to beta. So what this implies, that we have this gamma 1 and gamma 2 here, and these are beta 1, beta 2. So we do not need to find the linear combination of gamma 1 now, because already the coefficients and everything is given. So we have to find the C and D. It means we have to find that how gamma 2 is represented in terms of beta 1 and beta 2. Okay, so that is what we have to find here. So let us start with that. And if you have any doubt, please write it in the chat, or please unmute yourself and you can ask the question. So for second part, that is finding C and D, what I have to do is I have to just write gamma 2 in terms of beta 1 and beta 2. So what gamma 2 is equal to what I have, C beta 1 plus C beta 2. And then what this is 2 comma 4 comma 2 is equal to C 1 comma 2 plus D 3 comma 4. So what this implies, that 4 is equal to 1C plus 3D, and this and 2 is equal to 2C plus 4D. And now I have to solve this system of linear equation. So from here what I get, C is equal to 4 minus 3D. So this I substitute in this second equation and I will get 2 is equal to 2 4 minus 3D plus 4D, and this will give me 2 is equal to 8 minus 6D plus 4D, and this is minus 2D, and here it will be -6. So D is equal to 3. And once I have D is equal to 3, since C is equal to 4 minus 3D, I get C is equal to 4 minus 3 into 3, which is 4 minus 9. So it is -5. Any doubts here? We are just writing gamma in terms of C beta 1 and U. This is D beta 2. And we just solved this linear system of equation and we got this. Please understand this and please let me know if you have any doubts, or if understood, please let me know that yeah, you have understood this. So no comments, so I assume that it is clear. So our ABCD, so just for the sake of making this answer complete, so A was this -3, B is this -5, and C and D are C is -5 and D is 3 here. Okay. So we'll move to second question now. Question 2. So this is related to the dual spaces and linear functional. So for a vector space, V, let V star denote the dual space of V, and what, check whether the following statements are true or not. So first is, for any vector space V, we have dimension of V less than equal to dimension of V star. So this is our question, that we are given that V is a vector space and V star is its dual space, and we have to check whether for any given vector space V, dimension V is less than equal to dimension of V star or not. V star means the dual space of V. So I hope you all know what is dual space of V. Okay, dual space of V is the space containing all the linear functional of V. So when I say linear functionals of V, means it is, okay, so let me write this. V star is all the F from collection of all the F from this map such that F is linear map. Okay, so this is V star and this forms a vector space. One can check that as well, that when we add two linear functionals, we get a linear functional. So we can multiply it from by a scalar multiple from R, and it will again be a linear map. And the zero map, that is every element of V, every element of V going to R, going to 0, is the identity element of this vector space, the 0 of this vector space. Any doubts? I hope you all know the definition of V star. So this is the definition of V star. It is set of all linear maps from V to R. This forms vector space. And now we are asked to check that whether dimension of this V is less than equal to dimension of V star or not. Any guesses whether this statement is true or false or anything?
Didn't we do that V star is an isomorphic to V? So we
Oh, yes,
proved
but
it
when we
result.
say that, that is for finite dimensional case. I mean, what you are said is from the lectures.
Yeah.
But that happens when. But here we are not given any information that whether V is finite dimensional or not. So V could be anything. It could be infinite dimensional as well. So in that case,
So the
what will
basis would be not relevant here.
yes.
Yeah.
So it so yeah it so the question here is whether it will be uh bigger than the basis of V or not. Okay, so they are not saying that it could be like we have to check this inequality. Okay,
Hmm.
the dimension of V, whether it is always smaller than the dimension of V star or not. We have to check that. So let us start with the so we have the information about V, we do not have the information about V star at this moment. So let us start with the vector space V. Okay, so let V be a vector space and beta. So beta could be even infinite dimensional. So I am taking this I be a basis of V. Okay. So I'm starting with the basis of V. It could be and I is just any index set. Okay. So this is my setup and I have to check now whether I can get independent set. So first of all, we have to check about the we are talking about the dimension of V star. So it is about the cardinality of the basis. So we don't need to get so when I talk about the cardinality of dimension vector basis, it is enough to produce a linearly independent set of certain cardinality. If I can produce the linearly independent set of cardinality equal to beta, then I can always say that the basis will have at least that many elements in it, right? Because we know that the that cardinality of basis is the maximum cardinality of any given linearly independent set. So I have the beta, then I will produce this set of this map. So let fi we define this map fi from V to R. Okay. And how we define this? That beta I is going to suppose let gamma or this delta is basis of R. Okay. So this beta is going to delta and rest beta j going to 0 for I not equal to j not equal to I. So it is like only the ith element. So we can define any linear map on the vector space V by defining where the map of a basis element go, where the image of basis element is. Okay, so I'm using the basis of V to define this map F. And I'm defining it like this, that beta is going to delta and beta j is going to 0. Okay, so this is a linear functional. Okay, we can check that this is linear functional because when I add two element from beta I, so let me check that alpha V plus V1 plus V2 will be what? Then it have some coefficients from beta I. So if beta I is there, then it will be coefficient of that beta I and rest will be going to 0 and so on. So this you can check that Fi is linear functional. Under this, we can check this. Okay, it will be a linear map because any V1 and V2 will have information of we can write those V1 and V2s in terms of beta i's, and then when I evaluate Fi on it, I will get the element. You can check this clearly. Then this set, this Fi, I claim that this set Fi such that I in I is linearly independent set. Okay, if I do that, then I can say that basis has cardinality at least the cardinality of I, which was dimension V. Okay. So how can I show that? So when I have to show that some set is linearly independent, what I do is I start with the subset and prove that any linear combination if I take which is equal to 0, then each coefficient is equal to 0. So start with that. Let F1 to Fm belongs to, let me call this set gamma, gamma, okay? And consider that A1 F1 up to AM Fm is equal to 0. Okay, so what this F, when I write A1 F1 plus AM Fm is equal to 0, it is linear combination of functions. Okay, so, and it operates from V and goes to R. Okay, so domain is V and it is going to R. So if I produce, so let E is this element, beta 1 plus beta m. So I'm taking corresponding indices and I'm producing this element, E. Okay, then what is A1 F1 plus AM FM of E? It is 0 because we are assuming this is a 0 map. Okay, but if I evaluate this, what is this? A1 F1 plus AM FM plus beta 1 plus beta m, which is equal to 0. And this is what? A1 F1. And when I evaluate this beta 1 to beta m, F1 will only map beta 1 to beta 1 and rest will go to 0. So F1 of this element E is beta 1 itself. So this is beta 1. Okay. And similarly, A2 and F2, when it maps on this element, beta 1 will go to 0, beta 2 will go to beta 2, and rest will go to 0. So this is again beta 2. And similarly, AM into FM, now again when operated on this B1 to BM, I get beta M and it is 0. But now these beta 1, beta 2, beta M are elements from this basis of V. So they are linearly independent. Okay. So what does this imply? That A1 is equal to A2, everything is 0 since this beta 1 to beta M subset of beta, which is basis of V. Okay. So this has to be, the linear combination has to be equal to 0. I mean, the coefficients has to be equal to 0 since a beta 1 to beta m are in linearly independent set. So therefore, this F1 to Fm are linearly independent. Okay, because we started with the linear combination of F1 to Fm and we got that all the corresponding coefficients are 0. Then this F1 to Fm becomes linearly independent. Therefore, my gamma is linearly independent set. Okay. And when I have this has cardinality of gamma is equal to cardinality of beta, right? But this is just a linearly independent set in V star. So gamma is linearly independent set in V star. Therefore, cardinality of gamma is less than equal to dimension of V star. Okay, and but what is this? Cardinality of gamma is equal to cardinality of beta. But cardinality of beta is what? It is dimension of V. So what we got here, that dimension of V is less than equal to dimension of V star. Okay, any doubts here? So we
Hello.
started with the any vector space. We started with its basis and corresponding to each basis element, we introduced or we defined this map Fi, and which is linear functional, and we proved that this set containing all these Fi's is linearly independent. So basis will definitely have either this many elements or it might have few more elements, but it will definitely have at least this many elements. So from that we can say that cardinality of this gamma is less than equal to dimension of V star, because basis is the maximal linearly independent set. I mean, when I say maximal in terms of cardinality. Okay. Any doubts or any query like how things are going or anything which is not clear, please let me know.
Hello.
Yes, sir.
Amen. I can't understand that whenever you write down that A1 F1 plus up to so on AM FM and beta 1 plus beta 2 up to beta n equals to 0, then you have to write here A1 beta 1 plus A2 beta 2 plus AM beta n. Can you?
Okay, so what my aim is, I want to prove that, so I want to arrive at the conclusion that A1 to AM is equal to 0. So how can do? So this is map, right? When I write this A1 F1 plus AM FM is map from V to R, okay, such that each element of V is going to 0. When I write this, that A1 F1, so that map is 0, that it is mapping everything to 0. Okay, but what this E, this belongs to V, right? This beta 1, beta 2, beta m. Beta I was the basis of my vector space V. So I'm choosing this. So F1 to Fm are fixed. So I am taking corresponding indices and I'm generating this element E, beta 1 plus beta 2 plus beta 3, beta m. And this is in V. And what is this? So when I evaluate my this function A1 F1 plus AM Fm at E, I will get it is equal to 0 because this is E0 function. We are assuming. So these are all functions, this F1, F2, Fm. Because they are elements of V star, dual space. Dual space is set containing linear functionals from V to R. Is it? Yes, sir. So I'm.
Can you show some pictures? This is whenever we teach the students and some figure out some figure drawn कि one element this map करता है map to another element.
Okay, so let me show you one thing. Okay, so
Okay.
if this E is not clear, let me start with this. I have this A1 to F1 to Fm. Okay.
Okay.
This function A1 F1 up to AM Fm is from V to R, right?
Yep.
Okay. We have this. And what is V? V beta is basis of V. Okay. Basis of V.
Yep.
And beta is what? It is beta 1. Oh, sorry. It is beta I in R. Okay.
Yep.
Now I want now let's do this. A1 F1 plus AM FM. I evaluate it at 0. Sorry, beta 1. Beta 1 is element of V, right? And
Yes.
I'm and how this map is, I'm assuming that this is 0, that A1 F1 when I'm writing this is equal to 0, I am in this, that this is map from V to R such that V is going to R for every V. Every element of V is going to 0. This is my map. Beta is basis and this is how it is. So I am evaluating this at beta 1. Okay. And this is 0. I know because if beta 1 is in
Yep.
V and everything is going to 0. And now see what? This beta 1 F1 beta 1 plus A2 F2 beta 1 up to AM FM beta 1 is equal to 0, right?
Yeah.
Yes. But
Okay.
now A1 F1 beta 1 is beta 1 itself. That's how I have defined these FIs. FIs are such that the same index goes to delta or and rest or delta. Okay, if it is going to delta, then let me write this. It won't be this. It will be delta everywhere. Delta beta 1, delta or delta
Delta
just. Yes, it will be delta here. And now this will be delta and
A1 plus A2.
even. Okay, so let me write this. Delta plus A2 into 0 plus up to AM into 0, which is 0. So which is what? Delta, A1 delta is equal to 0. But delta is non-zero. That I know.
So A1
Okay.
equals to
Delta is non-zero because it is basis of R. So this implies what? That A1 is equal to 0.
okay.
Okay. So A1 is 0. Now I got that A1 is 0. Similarly, when I do evaluate that A1 to F1, again this A2 F2 up to AM FM on beta 2, I will get that again A2 delta is equal to 0, and this will be now A2 is equal to be 0 since delta is non-zero. And I can do this for m many since this is finite. Okay.
Okay.
Similarly,
And
I will get the A1.
on the previous line, you have write down the F1 beta 1 delta and
Yes.
F2 beta 2 0.
Yes. I think there was some error there. This is AM delta is equal to 0. This implies that AM.
No, but if I change it to delta, then how do I show that it's a subset of beta, which is the basis of V?
No, I'm not saying that. It
No,
is
no.
not
If you go
subset of
up,
beta.
no. If you go up a bit,
Yes.
no. If you go up, yeah, this particular since B1 to
Here,
BM is subset of B basis of V.
here,
No. After the delta thing,
this, this,
up.
up.
So yeah, this line,
Yeah,
even
this.
delta, yeah, this one.
We are in R now actually. So this is A1 plus AM. Actually, this won't help here actually.
Mm.
So delta is non-zero, A1 to AM is 0, something like that. But I think this is not helping us here. But this will definitely do. Because we are in R now. We have evaluated this at this element beta 1 to beta m and we got this. But yeah.
And how do I show that gamma is less than dimension of V star? It's still valid?
Yes, this is valid, right? I mean,
Okay.
okay, even if we forget this and we have this. So this is clear, right? So forget that. This is clear that when I
Yeah.
evaluate, I get everything is equal to 0. So since A1 F1 and AM FM is 0 and I got that A1 is equal to A2 up to AM is equal to 0. Okay, so F1 to FM is linearly independent. Okay, let me
Yeah.
explain this again. And this was any arbitrary. So this was F1 to FM was any arbitrary subset of gamma, right? Gamma which was Fi, I in I. Okay. This has cardinality. Cardinality of gamma is cardinality of I. Okay.
Mm.
So in
So
arbitrary,
earlier we used the cardinality of gamma is cardinality of beta. So that would change
yes,
things.
yes. And this
Okay.
is cardinality of
Okay.
beta
Okay. No. That.
because we have the same indexing set in both gamma and beta. So they
Mm.
are equal
Yeah. Okay.
actually.
Okay.
Yeah. So for each element of beta, I am producing an element Fi, and this is true for any index I. So, and we proved that gamma is linearly independent set. Okay.
Yeah.
And so cardinality of gamma will be less than equal to dimension of V star. This is true in
Mm.
okay. This is true for any vector space. Then cardinality of any linearly independent set is always less than equal to its dimension. That dimension is the maximal cardinality of any linearly independent set. But this is what? This is cardinality of beta because of this thing. And which is dimension of V star? V. So this implies that dimension of V is equal to, oh sorry, less than equal to dimension of V star. Is it okay now? So I think this won't help us, that evaluating it at this beta 1 to beta m. We have to do this only. Let's start with beta 1, then we will get a1 to be 0. And a1 is anyway 0 here. So here we need not even use f1 because a1 we already proved that it is 0. Any doubts now that we finally proved that this is linearly independent set and its cardinality will be now less than equal to dimension of V star? Sir, is it clear now?
Yeah.
Okay. Thank you for pointing this out because I maybe was thinking something else, but yeah, we have to go through this, that evaluated it at every beta i's and then obtain that, not every beta i's, this beta 1 to beta m, and get that all the coefficients are 0. Yes. Thank you. Yes. So is it clear now that cardinality of dimension of V, I mean the dimension of V is less than equal to V star? If you still have any doubts, please let me know. Otherwise, I will then move to. So this statement is true actually. This was true for any given vector space. And yes, so this is true. Any doubts now? If not, then I will move to next question. Even if you have any doubt or feel that this is not yet clear, then please let me know. Now, second question is that there exists a vector space V such that dimension of V is strictly greater than dimension of V star. And what is your guess? We just proved some statement for arbitrary V, and then this statement will be then any guesses?
Shouldn't be false.
It is false because we just proved that for any given vector space, this is false by above question or above. Let me write question. Because we proved that V was any arbitrary vector space, and we proved that for any given vector space, and it was whether it was finite, infinite, we actually didn't care. We just started with the basis beta I, and index I was any set of finite, infinite, or countable, uncountable cardinality. A third is that if V is finite dimensional vector space, then dimension of V is equal to dimension of V star. And any guess like this will be now? Any guesses? Somebody just, when I wrote the first question, somebody said that dimension of V is equal to dimension of V star.
Because of isomorphism.
Yeah, because of isomorphism. So in the lecture, we have already proved that for any finite dimensional vector space, dimension of V is equal to dimension of V star. And how they prove it, I will just quickly give the sketch of the proof. For V of dimension n, so V is finite dimensional, so we can assume it to be of dimension n. Then we define this map V from V star to M1 cross n R. Okay. And how it is defined? So V star contains elements linear functional. So they are all functions from V to R. R is one dimensional and V is now n dimensional. So corresponding to this F, I map it to its corresponding linear transformation matrix. And this is now n cross 1 matrix because the beta is the basis of V and gamma is the basis of R. So this is 1 cross n matrix. And for any matrix, 1 cross n matrix will define a linear transformation, and any linear transformation will have a basis or linear transformation matrix corresponding to basis. So this is isomorphism. This is isomorphism. This is already covered in the lectures. So therefore this dimension of then M1 cross n R is, we know, is n, is last time we saw in the lecture that it is 1 cross n, which is n in this case, and which is nothing but dimension of V as we had assumed. And since this V star is isomorphic to M1 cross nr, we know that finite dimensional vector space, they are isomorphic if and only if their dimensions are equal. So this implies that dimension of V star is equal to dimension of V from here. Is it okay? Or let me write this, is equal to dimension of M1 cross nr, which is equal to n. So since dimension of V star is equal to n, which is now dimension of V, this implies that V star is isomorphic to V. Now is this clear? This is already given in the video lectures. And
can you repeat the argument of why dimension of V star equals to dimension of 1 cross n matrix?
because this is isomorphism of finite dimensional vector spaces, and in
Okay.
finite dimensional vector space we have the proposition already proved in last week's lectures.
Okay.
That two vector spaces are isomorphic if and only if, it is if and only if statement, if and only if their dimensions are equal. So if F from V to W is isomorphism if and only if dimension of V is equal to dimension of W in finite dimensional case. And since we are in finite dimensional setup, what I did was I took this V star to M1 cross n R, and I proved that this is isomorphism. And since this is isomorphism, I know that dimension of this MNR, M1 cross NR, is n. And by isomorphism, I get that this will be now dimension of V star. And V star now has then dimension is equal to n, and this was dimension of V, so they become isomorphism. It is a proposition proved in last week's lecture. So I'm just using that. And if that is not clear, you can just go through this week's lecture. And this isomorphism, how this is isomorphism, it is also given. Okay, is it okay now?
Yes.
Yeah, okay, thank you. So this statement is true. Now next. For that, let V is, if V is isomorphic to W, then V star is isomorphic to W star. Okay. Any guesses now? again, now here V and W are not given any information that it is finite dimensional or infinite dimensional. If it was finite dimensional, then this would have been easy, because what we could have done is that dimension of V is equal to dimension of W, since they are isomorphic in finite dimensional. And since by previous result for finite dimensional case, dimension of V is equal to dimension of V star. So if for finite dimensional, the dimension case, V isomorphic to W, then dimension of V is equal to dimension of W. W also V and W finite dimensional, then dimension of V is equal to dimension of V star. Similarly, dimension of W is equal to dimension of W star. Okay, and using all these three, we can easily get dimension of V star is equal to dimension of W star, just following all the inequalities. And this will imply that V star isomorphic to W star. But this is easy when we have that V and W are finite dimensional. But if infinite dimensional V and W, then we can't say this. We don't have this dimension argument in that case. Then what is guess? So whether this statement is true or not, what is your guess that whether this statement will be true or not in infinite dimensional case?
Not over.
In the first problem, we did that dimension of V would be less than equal to dimension of V star.
Yes.
So we can use that result.
Yes, sir. But we are not now asked the dimension of
Yeah,
V
but
star
we
and
can
V.
still use that
Mhm.
result to say that uh, V is not isomorphic to V star.
Sir, but okay, so your argument is that V is isomorphic to W, but V star is not isomorphic to V. W star need not isomorphic to W. Then V star is not isomorphic to W star. That is not always true, right? Because I can have this, that I R2 or let me take R3 isomorphic to P2R. Okay, this is not isomorphic to R4, and this is not isomorphic to, just I'm giving the argument. This is not VV star. This has nothing to do with VV stars, and this is not isomorphic. But these two are isomorphic because these two have same dimension.
Mm.
Okay, so that dimension argument will not be useful here. Or let me keep this here. Like, I mean, so what can we do? We have to actual. So apparently, so let us start with this. So my guess is that yes, this will be true. So let me give you a quick proof. So let us define this phi. So since V and W are isomorphic, we can assume let P from V to W be an isomorphism. Okay. And then we define this the following linear transformation V star from W star to V star now. The direction has changed. How? That F, so V star contains all the maps from W to R, W star. So it is going to now F composed with phi. Okay, so F is what? It is from W to R, and F is from V to O. V not, it is from W to R, and it's now we are composing with something from V to W. So this composition is mapped from V to R. Is it clear? So this composition is from, like, phi is from V to W. Now F is from W to R. So we are just compositing. So using the isomorphism between V and W, we are now defining a map from W star to V. Is it okay?
Yeah.
Okay. So this is map. This is, and this is well defined, and this is also linear, linear map or linear transformation. So how, let us quickly check that for F comma G in W and W star, or and let alpha in R. We can take that phi star of alpha F plus G. I need to check that it is a linear functional, right? So this is mapped from V to R. So let us, yeah, this is mapped from, when I apply phi star, it is mapped from V to R. So phi star of alpha F plus G is what? Phi star. So let me write this. It is alpha F plus G composed with phi. And composition is like this, plus G composed with F. And now this is what? Alpha into F composed phi plus G composed F, and this is alpha. By definition, this is phi star of F plus phi star of G. So this phi star is a linear transformation, and that's why we are okay. So this is linear transformation from W star to V star. Okay, so let us now claim that. Now we can similarly define this V inverse star from V star to W, where we send F to F composed with phi inverse. So phi inverse exists, okay? Phi inverse exists as phi is isomorphism. So now I have this phi star in phi inverse star.
So in
And I
the
claim
above argument, you said that
Mhm.
G compose phi is G compose F. Is that correct?
Oops, here it should be phi.
Yeah.
Yeah, it is phi. And then it is phi star G. Thank you. Yeah. This is phi. Now similarly, this phi star, same argument we can do, and this phi inverse star will be now linear transformation. Is linear transformation. Okay. And we can claim that this phi composed phi star is phi inverse star composed phi star is identity V star, and V star composed phi inverse star is identity on W star. I hope both the identities are correct. So let us start. What is phi inverse star composed with phi star of F? It is what? It is phi inverse star F composed phi. And when I do apply phi inverse star on this, it is F composed phi composed with phi inverse. And then this is phi composed phi inverse. This is identity because phi and phi inverse are inverses of each other, as phi is isomorphism. And this is identity, and this is F. Similarly, I will get that phi star composed phi inverse star F is phi star composed with F composed phi inverse. and this is F composed phi inverse composed with phi, F composed phi inverse P, and this is F composed I, again I. So this is identity. These maps are identity on corresponding V star and W star. So therefore this, we know that if I get to a linear transformation such that ST is equal to I and TS is equal to I, then they are invertible, and therefore this P star is isomorphism. Okay, because we got the inverse, that P star inverse is actually P inverse star. This is what we got, that P star is invertible, therefore isomorphism, therefore V star is isomorphic to W star. Any doubts here? We actually proved that these both vector spaces are equal, isomorphic. So we need not have the information about the dimensions. We can just, this phi star and W star argument is true even for the finite dimensional cases. So this statement is true. Okay, so since apparently it was, I hope it is clear now that why this is isomorphism. The dimension of V and V star could be different. But if I have two isomorphic vector spaces, then their corresponding dual spaces will be isomorphic. That is my argument. Is it clear? So if two vector spaces are isomorphic, then their dual spaces are also isomorphic. The spaces itself need not be isomorphic because we got that the dimension was less than equal to V star. But yeah, the corresponding dual spaces are isomorphic if the V and W are isomorphic and so on. Is it clear, or is there any doubt here, like how things are happening?
Hello, I have a small doubt.
Yes, sir.
You have mentioned that for actually two cases. In question 3, it is said that dimension of V is equal to dimension of V
star.
dual space V star.
Mm-hmm.
But for question 2, dimension of V is less than or equal to dimension V star. So what
Yes,
is the
sir.
condition in join slightly late? For question 2, what is the condition actually under which it is less than dimension of V star?
Sorry, sir. What you are saying is, what is the?
For question 2,
Mm-hmm.
is less than or equal to dimension of V star. So under what condition it is?
Okay, so you are asking that under what condition it will be strict inequality.
Yes.
So if in finite dimensional case it is always equal, in infinite dimensional case they are like, there is strict inequality. That is from, we can conclude from question 1 and 3. This is always true. The dimension of V is less than equal to dimension of V star. This is always true. This is true for
Always
any vector space.
Yes.
Yes. So from this, we can immediately say that this is not possible because we already proved that for any given vector space, this dimension is always less than equal to dimension of V star.
Okay, thank you.
Yes. And this is, let me write this also, for above statement is true for any vector space P. So there does not exist any vector space such that the other way would happen, because we already proved that V is always less than equal to, dimension of V is always less than equal to dimension of V star. So this second case will never happen. This is the second question is just negation of the first one. Not the negation, but yeah, contrapositive kind of stuff.
Can I tell
So
that for an infinite dimensional vector space, dimension of V is less than dimension of V star?
Not less.
we
Less
can
than
s-
equal.
we can not, I mean, there could be examples where it is equal, or there could be examples where it will be strictly less than. I mean, we can't say directly from this statement at least. This just say the dimension of V is less than equal to dimension of V star. In case of finite dimensional case, they are equal, but infinite dimensional case, we can't conclude from this. That we can't say if and only if for infinite dimensional case that it will always be strictly less than dimension of V star in case of infinite dimensional case, because there could be maybe cases where they could be equal. I mean, I do not have examples for those two at this moment. But yeah, we can at this moment we can't conclude about the dimensions in case of infinite dimensional spaces.
Okay. Okay, thank you.
Yeah. But this is okay, right? That V and W are isomorphic, then V star and W star are isomorphic. Okay, so let us go to next question now. If you have any doubt, please ask. I'm Otherwise, I will move to the third question. Question 3 is that let T from MNR to R be defined by T of A is equal to trace of A. Okay, then check whether true or false. First is that T is a linear functional. That T is a linear functional. And when I say linear functional, I mean it is a linear transformation where codomain is R. So again, we know how to check if if a map is linear transformation or not. We start with A and B and C in R, and then T of A plus or CA plus B is equal to trace of CA plus B is equal to trace of CA plus trace of B. Trace is additive, so we are using that property of trace here, and this is trace of A. We did this quite a few times in last few lectures, so this is nothing but T of A plus T of B, and that's why T is linear transformation, and therefore it is linear functional. Any doubts here? That T is linear functional. Understand that T, when I say linear functional, it is just a map from vector space to R. So is it okay? So this statement is true, that this is linear functional. Now, any doubts? I don't think like this is we have done quite a lot time in previous lectures. So second is that T cannot be 1, 1. Any guesses here? T cannot be 1, 1. When I say 1, 1, I mean injective. Any guesses that T cannot be 1, 1? T cannot be injective map. Note that n is anything in natural number, okay? Let me write this here. So can we say that T can never be 1, 1 for any given n? Map is defined, T is defined. What is changing is M and R.
No, because it doesn't work that way, right? Because trace, that means trace is same, but matrices may not be same. So
Yes, I mean, but if I take n to be 1, then my M1R is just set of this, right? And my T then from M1R to R will be,
injective.
yes, it will be just this map. And this is injective. This
Oh,
is injective, bijective, and everything. They are saying T cannot be 1, 1.
cannot.
That
So
for
it's for
any given
it not even one case, but there's one case. Yeah. Okay.
it is cannot be 1, 1, can never be 1, 1. But we
Okay.
have a case where this is 1, 1, so this is false. Okay, we got an example where this is holding that T is 1, 1. So any doubts here? For T greater than, for
Ma'am,
n greater than 1, this will definitely.
can you
Yes, sir.
explain this again?
Sorry.
Can you explain this? T cannot be 1-1 injective map. Again, I explain for you.
Okay, T cannot be. Okay, so they are saying that T cannot be 1, 1 map for any given. Oh, let me write this. T cannot be 1, 1 map for any given n in n. So they are saying that T cannot be 1, 1. So when I am to say that T is true or false, if I am to say that T is true, then I had to start with any MNR and prove that T can never be 1, 1. And if I am to say that T is this statement is false, I just have to give one example saying that T is 1, 1. And the moment I show that T is 1, 1 for some n, then this statement becomes false because we got that if n is 1, then MNR is M1R. M1R is 1 cross 1 matrices, which is these matrices 1 cross 1. And then T from M 1 cross 1 R to R is just A going to A. I mean, this matrix A going to A. And this is injective map, right? Because T of A, if I am taking T is equal to T of B, then this will imply that A is equal to B. And again, that A, if A is equal to B, then A is equal to B. This is the simple argument. Therefore, T is injective. Is it clear now?
Yeah.
Okay. Injective or 1, 1 map. Okay. So third map, that T is always onto. Now they are asking the ontoness, or if you don't know what onto means, it means that T is always surjective. And what is your guess in this case? It is always surjective. So T is from MNR to R, right? T is from MNR to R such that A going to trace of A. And what is your guess whether this is surjective map or not? For any given n, it is always
Should
onto.
be.
Yes, it should be. Let me write this for more clarification. So because for any given this, so I want to show that this is onto. So I have to start something from the codomain and I have to produce a pre-image corresponding to that element. So let A be in R. Okay. Then we define this, let's say EA matrix where first entry is A, rest is 0. We can always define this matrix, right? For any n cross n. In case of 1 cross 1, it will be just A. In case of 2 cross 2, it will be first entry A, rest are 0. A22, A12, A21, all are 0. So we can always define this n cross n matrix EA. And then T of this EA will always be A. Is it clear? So for any given A in R, I can always produce such matrix EA and such that trace of EA is A. Therefore, T is onto or surjective map. Okay. Any doubts here?
No.
Okay. So this is when we are saying that this is true. So we proved this for any given n. This is true for any given n. And I think it has last. Yeah. Fourth is that rank of T is 1. Okay, so rank of T is 1. How to find that? So we use dimension theorem that dimension of V is rank T plus nullity T. And to find the nullity T, we have to find the null space, that is A belongs to MnR such that trace of A is 0. And if you remember that we did this quite a lot time, I comma j from 1 to n in MnR such that A11 plus ANN is equal to 0. And from here we were saying that A11 is equal to minus of A22 up to ANN. And so this was then, everything else was independent except for this A11 entry. So this is what, that Aij I comma j from 1 to n such that Aij belongs to R for I greater than 1, j greater than 1, and A11 is what, minus of A22 plus ANN. Okay. So this, the dimension of this null T, which is our nullity T, is what, n square minus 1, because these are n square elements minus this A11. Only A11 is linearly dependent in this case. So this was dimension. I mean, you can also go through the previous lecture notes or these live recordings of these sessions. There we have explicitly worked on this, that finding the subspace of MnR where trace of A is 0. And we have obtained this. Then by dimensional theorem or rank nullity theorem, what we have, the dimension of MnR is equal to rank of T plus nullity of T, right? And dimension of MnR is what we know is n square. This is rank of T plus nullity of T is n square minus 1, and this gives me rank of T is equal to 1. And this is true for any MnR. So is it clear now?
Can you please explain once more how it became n square minus 1 dimension of
Okay, n square
nullity?
minus 1. So let me show you like this. So if I have any matrix, so let me show you for 3 cross 3. It is A, B, C, D, E, F, look, G, H, I. Okay. It is this matrix. And I have to make it trace 0. Trace 0 means, trace of A is 0 means what? A plus E plus I is equal to 0. So what I do, A is equal to minus of E plus I, right? So I can do, choose this all to be any element. And A I fix to be minus of E plus I. Then all these elements, so then this element, let me explicitly write this. Minus 1, 0, 0, 1, 1, minus 1, 1. This, comma, minus 1, 0, 0, 0, 0, 0, 0, 1, comma, this, everything, 0, 1, 0, 0, 0. This and rest all elements. I mean, let me write it in one go. B, C, D, E, no, E. It's gone. F, G, H. This will form a basis. I mean, you can separate all these variables. So this 6, 7, and 8. So this was 3 cross 3 matrix. These are 6 components: B, C, D, F, G, H in R. And these 2 elements will always give me trace 0 matrices. These 3 entries here were independent. I don't care what is happening to non-diagonal elements, non-diagonal entries. I want to only take care of the diagonal entries of a matrix for it to be a trace 0 matrix. I mean, I hope I'm clear that this is trace 0, right? For trace to be 0, I only care about these 3 elements, right? And I want to make them 0. So if I make one of them minus of summation of others, it will give me 0. Is it clear?
No, whether for this case it will be n square minus 1 is the nullity.
Yes.
What will be the value? Nullity for 3 into 3 matrix.
Yeah, this is for 3 cross 3. It is n square minus 1, right? 8 elements. Here 6 plus 1 plus 1.
Oh, okay.
Yeah. I mean, I'm just writing this. Actually, when I'm saying B, I mean this matrix 0, 1, 0, 0, 0, 0, 0, 0, and so on. Okay.
So in the second basis matrix, I think -1 should not be there.
It will be there. Here, it will be there. Here, it will be -1. And it will be, then only it will add up to 0, right? For example, this element, for it to be
Okay.
inside trace 0 element, it has to be -1. Otherwise, this element itself will not be in our desired vector space or vector subspace. And we will fail there. Okay, so -1 will be there. Yes. When I write this is what I mean. Okay, is it? I hope this is clear. I mean, if it is not clear, we went through this earlier when we proved, we covered the examples for vector subspaces. Okay. And question, just a second. That question 5 or 5th part of this is that there is an n such that T is invertible. When I say T is invertible, I mean that T is isomorphism. The dimension of MNR and R to be equal. So we already proved here that T is always onto, and for n is equal to 1, T is also injective. So T is bijection. For n is equal to 1, T is bijection, and therefore T is isomorphism, and hence invertible. Okay. We already proved that for n is equal to 1, T is injective and surjective. Surjectivity is true for any given n. Injectivity we proved for n is equal to 1. Is it okay? Okay, so this was it. I mean, I hope this was clear. And we'll move to now next question. Question 4, that let V and W be finite dimensional vector space over R, and V cross W denotes the product space. and let U be a subspace of V, and V by U denotes the quotient space. And we have to check the following: true or false. Okay, the first question is now the dimension of this product space V cross W is dimension of V into dimension of W. Okay, any guesses whether this is true or false or what this is?
Should be dimension of V plus dimension of W.
Yeah, exactly. So we already proved or it is already covered in the lecture that this proposition which says that let V1, V2 up to Vn be finite dimensional vector spaces. So finite dimensional is important thing here. Vector spaces. Then spaces over R. Then dimension of V1 cross Vn is equal to dimension of V1 up to dimension of Vn. Okay. So this is already proved in the lectures. So therefore what we get that here we have n is equal to 2 and our V1 is V and V2 is W, and this gives me is equal to dimension of V plus dimension of W. And this is definitely not equal to V into dimension of V into dimension of W. So that's why this statement is false. Any doubts? Like this is direct implication of this proposition, which is proved in the lecture. And once I have this, the second question is trivial, that they are asking whether dimension of V cross W is dimension of V plus dimension of W or not. And this is, oh, let me use this. This is true by above proposition. Okay, so please go through this proposition in the product spaces lecture. Is it clear? Okay, we'll move to next question now, that dimension of V by U is dimension of V by dimension of U. Any guesses here? Like whether this is true, false, or what this is?
This is false.
Yes, this is false, because again using the proposition again which is proved in lecture, we say that let V be a finite dimensional vector space. Sorry? Is someone saying something? And U be a space, be a subspace of V, then dimension of V by U is dimension of V minus dimension of U. And this is proved quite nicely in the lectures if you have gone through. I mean, they have defined a map pi, and then they proved the nullity is equal to U. I mean, null space is equal to U, and so on. And use the dimension theorem there, and we have obtained this nice result in the lecture. And using that, we can directly say that the dimension of U by V is dimension of V minus dimension of W, but dimension of U, which is clearly not equal to dimension of V by dimension of U. Okay, so this statement is false. And let me write then fourth is that dimension of V by U is dimension of V minus dimension of U, and this is true by above proposition. Okay, so dimension of V by U is dimension of V minus dimension of U. It's not division of the dimensions. Is it clear? Please go through this theorems and its proof for better understanding of these propositions. Okay, and this is last for this, that let x and y be in V, and then we have that x plus u is equal to y plus u if and only if x minus y is in U. And what is your guess? Somebody saying someone? What is the guess here? They are saying that x plus u is equal to y plus u if and only if x and y in U. When I write x plus u is equal to y plus u, so they are all cosets. So x plus u is x plus u such that u in U. So it is actually a set which is represented like this. Okay, and they are saying that these two sets are equal if and only if x minus y is in U. And what is your guess now? Sorry?
Yeah, that's true because it would be an affine subset.
Yes. So we will prove this through the set inequality and everything. So the first thing that we have that x plus u is equal to y plus u. Okay, we suppose we are given this. We have to prove that x minus y is in U. Okay, so let A belong to x plus u. So this imply what? That A is equal to x plus u for some u in U, right? And similarly, and since x plus u is equal to y plus u, this imply what? That A belongs to y plus u. And A belongs to y plus u means what? That A is equal to y plus u dash for some u dash in U. So this imply what? That x plus u is equal to y plus u dash. And this implies that x minus y is equal to u dash minus u. But this u dash minus u is element in U since U is subspace. Therefore, we got that x minus y in U. Any doubts here? We just smartly played with the element A and we got this. That we started with A in x plus u. Then A is of this form, x plus u for some u in U. And but since x plus u is equal to y plus u as per the given condition for this first implication, uh, we get that A in U plus y plus u. And then I can write that A to be y plus u dash for some u dash. And since A has these two representations, I can simply write that x plus u is equal to y plus u dash, and we get that x minus y is equal to u dash minus u. And u dash minus u is in u since u is subspace. And therefore, we got that x minus y is in u. Any doubts here? I hope. Please let me know if you have any doubt. Okay, now second implication, we are given that x minus y is in u. So for any a in x plus u, we have that a is equal to x plus u for some u in u, right? And I can just add and subtract y there, x minus y plus u, right? And this is what a is equal to y plus x minus y plus u. And now this element here, this element x minus y plus u is in u, since x minus y is in u and small u is in u, right? So this imply what? That this a is this element x minus, let me write again, u. This belongs to y plus u by the definition itself. And similarly, if I take any element b in y plus u, similarly, if I take b in y plus u, then this implies again that b is some y plus u dash, where u dash in u. Then again, I will do this plus minus x, y plus x. Sorry, y plus x minus x plus u dash, and this b, then I can just shuffle and write this as x plus minus x plus y, which is minus of x plus y, x minus y plus u dash. And this is now element in u, so this implies that b belongs to x plus u. Any doubts here? And since this, I got that both the set are subsets of each other, I can say that x plus u is equal to y plus u. So when I do this implies that x plus u is contained in y plus u. And when I do this, I mean y plus u is contained in x plus u. And just following the set inequality, I get that this set, two sets are equal. Any doubts here? If not, then we'll move to next question. Question 5, that let V be a finite dimensional vector space over R, and U be a non-zero vector space or vector subspace of V. And they are saying that let V1 to Vn belongs to V with n greater than equal to 2. So these V1 to Vn are at least 2 elements. Then check whether following statements are true or false. So first is that if V1 to Vn is basis for V, then V1 plus U, Vn plus U is basis for quotient space V mod U. This is the question. What is your guess? That if I have basis V1 to Vn for V, then this V1 to Vn is basis or not? Anyone? Any guesses? Okay, so the answer is false, because if we have basis for V, this need not be basis for quotient space V mod U. Because first thing is that we know dimension of V mod U is dimension of V minus dimension of U. So if this has to be a vector subspace, and they are given that V is non-zero subspace of V. Okay, so note that since V1 to Vn is basis of V, this implies the dimension of V is n. Okay, and U is non-zero subspace of V, then dimension of U, this is U, is greater than equal to 1, right? And what is dimension of V mod U? It is dimension of V minus dimension of U, right? And so this is what? N minus dimension of V, which is what? This is something A, such that this A is greater than equal to 1. So this is strictly less than n, right? And what this set? So this set V1 plus U plus Vn plus U has, so if I call this set S, then cardinality of S is n, but dimension of V by U, we got that it is strictly less than n. Therefore, this set S is linearly dependent, right? So any set with the cardinality greater than the basis, cardinality of basis, is linearly dependent set. A dependent set, yeah. Therefore, this S is not a basis of quotient space V by U. Is this understood, that this A dimension of U, if we call this A, is greater than equal to 1? Since U is non-zero space, it has some non-zero element, and we can extend that element to a basis of U. This is basis replacement problem. If you remember, we have this in, I think, first or second week, that given a linearly independent set, we can extend it to a basis. And that is what we have got here. So this is kind of dimension, or using results, that V1 to Vn is basis. The dimension of V is n, and U is non-zero space, so it will have non-zero element, so its dimension will be at least 1. And we know dimension of V mod U is dimension of V minus dimension of U. This is n minus a, and a is greater than equal to 1. So this element n minus a is strictly less than n, because a is at least 1. So therefore this set S has cardinality n, but dimension of V mod U is less than n, as we have obtained from here. So therefore S has to be linearly dependent set. Therefore S is not a basis of V. Okay, is it clear? Please let me know if this is not clear. Sorry. Okay, so I assume that this is clear. Since if you still have any doubts, please let me know. Now what they are saying, that if V1 to Vn is a basis for V, then V1 plus U, Vn plus U is a spanning set, spanning set of the quotient space V mod U. Okay, so what is your guess here? That now V1 to Vn is basis, but now they are not talking about the basis. So this V1 plus U, V1 to U is not a basis. They are asking whether this spans our quotient space U mod V, V mod U or not. And what is your guess here? Any guesses?
नंबर पे कर रहा हूँ कोई नहीं इसके अंदर हम्म
Any guesses?
Yeah, it should span the
Yes, it should span.
module.
Because yes, as sir said, that it will span. Because see, any element, so let V plus U belongs to V mod U. Okay. Then this corresponding V, this belongs to V, right? And since V is a base, I mean this V1 to Vn is a basis. So this implies that we can write this V as V1 plus some A1 V1, A1 V1 plus so on up to AN Vn. So this imply what? Then I can write this as A1 V1 and so on up to AN Vn plus U, right? I'm just writing V plus U as this V expression of V plus U. And this is what? V plus U, then what will be? This is A1 V1 plus U. This is the definition of addition in quotient spaces. AN Vn plus U. And this is A1 into V1 plus U plus AN into Vn plus U. Right? So this implies that we can write any element V plus U from quotient space as a linear combination of these elements. So therefore, this V1 plus U and so on up to Vn plus U is spanning set of quotient space V mod U. Is it okay now? We can express any element V plus U from quotient space as a linear combination of these elements V1 plus U, V2 plus U, and so on up to Vn plus U. Is it clear now? Please let me know if there are any doubts.
How it comes from a1 v1 plus u to a1 bracket of v1 plus
This is
u.
definition of vector quotient space. I mean, this is definition of addition in quotient space. They do like this. So a plus u plus b plus u. So these are elements in quotient space is equal to a plus b plus u up to representation. But this holds. So this is addition in v mod u. So I'm just splitting this. So this is equal. So I'm just splitting this here. And this is also true. So if I have some c plus a here, oops, let me write here that c a plus u is equal to c a plus u. This is also true in quotient space. This is a definition of the quotient space, how the addition and scalar multiplication defined in the quotient space. Okay, any doubts?
So previously we proved that this is not a basis for receiver.
Sorry, sir?
This first previous to this, we have shown that this is not a basis, right?
Yes, this is not a basis, but this is spanning set.
No,
Basis
if
is
it is
spanning
not
set
a,
along with the linear independence. So linear independence is not hold in general, but spanning, yes, we can say. And also that it is given that v1 to vn is basis for v, then thus this v1 plus u up to vn plus u is spanning our quotient space. Yes, sir. Any doubts? I mean, this was the question or something else?
no, this only. Say the spanning means it should be a basis, right?
No. Spanning set means it should just span. Span means that I should be able to write any element. For example, that I say that
Okay, we have to prove only it is linearly independent.
the linear independence is not said when we say spanning, that this, for example, let me just write that this 1 comma 0 0 comma 2 3 comma 0 is spanning set of R2 very well. This is spanning set of R2. It spans. I can always write a comma b is equal to a 1 comma 0 plus b by 2 0 comma 2 plus 0 3 comma 0. It is spanning. Span means that's it. I should be able to
No,
write
it is
any
span, but
element. Yeah.
no, but here if only 1 comma 0 is there, then you cannot span, right?
Sorry?
If only 1 comma 0 is there, now three bases you have written. No, there are
Huh.
three sets is there, right? If suppose 1 comma 0 alone is there, then it cannot span R2, right?
It cannot span. It cannot
So
span.
that's what earlier we proved the dimension of V by U is less than n, right?
Yes.
If it is less than n, the okay.
Yeah. It was basis. We were talking about basis. So it has to be linear. So basis means spanning set along with linearly independent set. Okay, so so this set was not linearly independent because we also have that proposition that any set of cardinality greater than the dimension is always linearly dependent. That is also proved. So a dimension of V mod U or
Okay,
the
okay,
quotient space
yeah, I
is
understood.
less than
Okay,
n.
already
But this,
we proved linearly dependent, so it is have more cardinalities. It can span. So, okay,
yes. It
okay,
need not
yeah,
be
yeah, okay,
linearly
that's
independent, but it can span. It can
yeah,
definitely span.
okay,
So
okay.
yes, but so once but one of them is dissatisfied, it is not a basis. Okay, so I hope that is clear. Then Yes, now this one is okay. We have a few minutes. If set v1 plus u up to vn plus u is linearly. So just a second, let me. So this is clear, right? So this statement is true. I hope. Just writing for clarification. Is linearly independent set in quotient space v mod u. Okay. And then they are asking that whether this v1 to vn is linearly independent in v or not. Set. Linearly independent set. Okay. So they are given now that a set is linearly independent in quotient space. Now they are asking whether in our original space V, whether it is linearly independent or not. And what is the guess? So let us, since we are asked about the linear independence, let us assume that A1 V1 up to AN Vn is 0. Since this is 0, then A1 V1 plus AN Vn plus u is equal to 0 plus u, right? And this implies what? That A1 V1 plus u. Now just using the definition of addition in quotient space, I get this. And this imply what? That A1 V1 plus u up to AN Vn plus u is equal to 0 plus u, right? But what I know that this set V1 to Vn, V1 u plus V1 plus u up to Vn plus u is linearly independent. So this implies what? That A1 so on up to An is 0 since V1 plus u, Vn plus u is linearly independent set. Okay. So we started with a linear combination of V1 to Vn and we arrived that V1 to Vn is equal to 0 and we got that all the scalars or all the coefficients of V1 to Vn are 0. So this implies that this set V1 to Vn is linearly independent set. Okay. Is it clear? So if V is linearly independent, this set V1 to V1u plus Vnu in quotient space, it need not be linearly independent. However, if I'm given a linearly independent set in the quotient space, then corresponding VIs will form linearly independent set in my original vector space V. Is it clear? So this statement is true. Any doubts? Okay, so I assume that there are no doubts. So let us just this next question. Let us quickly we will go to this question. Let V is equal to P5R P5R is polynomials with degree less than equal to 5. Okay. And let W is equal to P in V such that P of 0 is equal to P of 1. Okay, so when I take polynomial P in V, that is polynomial of degree 5, when I evaluate it at 0 and 1, they should be equal. So this is my vector subspace, be a subspace of V, and W is equal to P in V such that P of 0 is equal to P of 1. Now I say that the P of 0 is equal to P of 1, but at the same time it need to be equal to 0. So this W naught again be a subspace of V. And now I want to find dimension of V mod W and dimension of V mod W naught. Okay. So we clearly know that dimension of V mod W is dimension of V minus dimension of W, right? So we already know dimension of V means dimension of P5R here. And we discussed this last time, that dimension of any P and R is n plus 1. So here n is 5. So dimension of this is 5 plus 1, which is 6. Okay. So we just have to now find the dimension of W's and W naught. So let us start with finding dimension of W. So W means what? W is set such that P in P5R such that P of 0 is equal to P of 1. Okay, so let P in V, then P is of the form, P is what? P will be some A0 plus A1x plus A2x square, A3x plus A3x cube, A4x4 plus A5x power 5, right? And then P of 0 is equal to P of 1 means what? A0 plus A1x, A10 plus A20 and so on up to A50 is equal to A0 plus A11 plus A21. Okay, we are having x square, x cube, x4, but since we are evaluating it at 1, it is 1 square, again 1, 1 cube, again 1, 1, 3, and so on. So I'm just writing therefore A5, 1. So these imply what? That A0 is equal to A0 plus A1 plus A2, A3, A4, and A5, right? So A0 get cancelled and we are left with A1 is equal to, or A5 is equal to minus of A2, A3, A4 and A5. Oof. Minus of A1, A2, A3 and A4. Okay. So since this A1 plus, since we get cancelled, A1, A0 get cancelled and we get A1 plus A2, A3, A4 is equal to 0. And I'm just rearranging them again and I get this, that A5 is equal to minus of A1 to A4. Okay, so when I write this in W, so W is what? A0 plus A1x plus so on up to A5x power 5 such that A0 is cancelled. It means A0 is independent. Okay, so this means what? A0 is in R, but and A5 is what? A1 up to A4 in R, and A0, A5 is what? A1 plus A2, A3 and A4. Then what is dimension of this W? Dimension of W is,
5.
we are choosing A0 and this A1, A2, A3, A4. Then somebody said something. It is
5.
It is 5. Exactly. So dimension of W is 5 because we have choices for this A0 and this A1 to A4. Okay, so that's why it is 5. So then therefore dimension of V mod W will be what? Dimension of V minus dimension of W is equal to 6 minus 5, and then this will be 1. Okay, for those who are not yet clear like how this is dimension 5 and so on, you can just go through the video recordings of previous live sessions. There we have gone through like many examples where we have obtained dimension of subspaces, vector spaces, and also the one related to matrices. We have covered all that. Okay, so please go through those, and we have to now do for W naught. So W naught now, W naught is what? It is P in P5R such that P naught is equal to P1 is equal to 0, right? So we already know that when P naught so there are two, sorry, it's not P naught, it is P at 0, P at 1, and it has to be equal to 0. So when I know that when this is happening, then I have only this condition that A5 is minus of A1 plus A2 plus A3, A4, right? From previous, by previous part of this question. We already have this, or let me denote this star from star. And but when I write this, P0 is equal to 0, this implies what? That A0 plus A1x, oops, A1 0, A2 0, and so on up to A5 0 is equal to 0. So this implies what? That A0 is 0. Okay. So now W0 is what I can say, combination of these two conditions. Okay, so my W0 becomes what? A0 plus A1x up to A5x power 5 such that A0 is now 0. Okay, so A0 is gone. This A1, A2, A3, A4 are in R, and A5 is what? Minus of A1, A2, A3 plus A4. So what is the dimension of W0 then? A0 is completely gone. So it is just this A1x plus A5x such that A5 is minus of A1 plus A2 plus A3 plus A4. Okay, and where A1, A2, A3, A4 are in R. Okay, so now dimension of W0, I have simplified it for you. It will be
4.
it will be 4 exactly. Then dimension of V mod W0 or V by W0 will be dimension of V minus dimension of W0, and it will be now 6 minus this 4, then it is 2. So this is the dimension of quotient spaces we have. I mean, you also have questions of this sort in assignments. So please do them carefully. And if you have any question, please ask right now related to this or anything which we covered so far in this session. Any questions? So these are the only questions which we can solve right now since we are anyway over the time. But still, if you have any doubts, please ask. I will go through it once again for you. And I would like to suggest that before like you can go through the lectures before trying to come for this problem solving session, and also once quickly go through the assignments given to you, so that it will be beneficial for you. Like you will have an idea like what kind of questions will be solved and so on. And it will help you to understand the problems more carefully if you at least know the definitions of the things which we will be using in the problem solving sessions. If you have any doubt, then please write it in the discussion forum. We will try to answer those. And also, if you felt that something was not clear with you, like how we were finding the dimension of subspaces, please go through the recordings of the problem solving session. It is there in the SWAYAM portal under problem solving session section. And you will have video recordings of all the previous lectures. You can go through those. And if you have any doubt, please ask me right now. And also PDFs are also available. So if you don't have time to go through the videos, you can just quickly go through the PDFs as well. So yeah, if no further doubts, I think we can end the session. If you don't want to talk, you can write the doubts in the chat. Otherwise, we will end the session.
Sorry, can you go to the proof of where we proved that V star is isomorphic to W star? I just need to
Okay, just a
note
second.
down a few
The
things there.
isomorphism to W star. Yes,
Yeah,
this
the
one.
second, third, the next page below.
Yes,
Yeah,
this. Yeah.
a little bit more. Sorry, I just need to note down a few things.
Okay.
Scroll
You can
down
note down. Okay.
more.
PDFs are also available. I mean, you can
Yeah,
note down,
just
no
one
problem.
or two
Yeah,
lines. It is.
sure. No problem.
If you can scroll down.
Down means up or down?
Down.
Here?
Yeah, yeah.
Okay, this one. Okay.
Yeah, this part. Yeah.
Other than this, any doubts? Any part where it was not clear how things are and so on? I think this will be from W and this will be from V. Because V is starting from W star to V star.
So change of base is
Sorry, sir. Change of basis. Okay, change of basis is just a linear transformation matrix for identity transformation from one basis with respect to other. So how it is? So if I have identity from beta to gamma, so what I do? So if beta is beta 1 to beta n, okay, and gamma is from gamma 1 to gamma n, then this I beta gamma is obtained. Uh, Sir, are you done writing this so that I can move to
Yeah,
next
yeah,
page?
yeah. It's done. Thank
Okay.
you.
Then I will write it in on new page. Uh, huh. So how we obtain the basis change matrix is this I beta gamma is just matrix like this, where the columns corresponding to beta 1, beta 2, beta n, oops, and these are columns, and rows corresponding to this gamma 1, gamma 2, and so on up to gamma n. And when I write this, what I mean that my base, I mean the domain is from beta and I'm now going to gamma. So what I need to do is, so if beta is this, so I want to write this beta i's in terms of gamma i's. Okay, so beta i's will be some, let me write this random number a1, gamma 1, and so on up to an, gamma n. Okay, I can write this, right? Because this gamma 1, these are basis of V. This is also basis of V. Okay, so I have this beta I. written in terms of gamma 1 to gamma n. Okay, every element we can express it uniquely in terms of basis element. So this is that expression. So when I write this, what I do is ith column will be this A1, A2, so on up to AN. Okay. So if I am to write B1 as A11 gamma 1 plus A21 gamma 2 and so on up to A N1 gamma N, then corresponding to beta 1, this column will be A11, A21, A31, so on up to AN1. And when I write this for each like this, AN1 gamma 1, AN2 gamma 2, ANN gamma N, then this is how this matrix is formed. A1N, A2N, ANN. Any doubts here, sir?
No, it is clear.
It is clear, right? So that's how. And even for linear transformation, we do the same. If I am asked to write linear transformation matrix from beta to gamma, I do the same thing. Instead of beta 1, what I do this beta 1 in terms of some gamma 1. Let me write again this, some A1, B1 or AN gamma N. Similarly, T beta N in terms of, let me write this, A11, AN1 and AN1 gamma 1 and so on up to I think I made some mistake in coefficients, but I hope you got the idea. Then again, I will write this T beta to gamma like this, corresponding to T beta 1, all the coefficients, beta 2, all the coefficients, and corresponding rows are corresponding coefficients of gamma 1 to gamma n. Is it clear?
Yes.
Okay. So that's how the linear transformation matrix and basis change matrix are. So when I do this for basis, identity transformation is like vector going to itself. So that's why this beta I is going to itself. So I'm just writing this beta I in terms of gamma and I'm getting this basis change matrix. This is basis change matrix. And this is linear transformation matrix or matrix of linear transformation. And what this matrix actually define is that suppose this T is from some V to W and T has basis beta 1 to beta n and this has basis gamma 1 to gamma n or m, then this T beta gamma, when I multiply this with elements from some element in Rn to Rn, then this A, B, C, and suppose N, or let me write A1, A2, AN, then I will get something right here. If this is M cross N matrix, this is N cross 1, I will get this M cross 1 matrix. Okay. And what does this imply? That this T of A1 beta 1, AN beta N is going to, here this is B1, B2, Bn, then it is going to B1 gamma 1 and so on up to Bm gamma n. This is what linear transformation matrix means. So linear transformation is just matrix, and this is what is the significance of this. So beta 1 to gamma m actually defines this. In terms of basis change matrix, it is just identity with this same cardinality on both the sides. Any doubts now for this linear transformation matrix?
It is clear.
It is clear. Okay, sure. Thank you. So I think we are over the time now. If you have any questions, please write them in the discussion forum or the Google group which we have. We will change the session and the video recording of this session and notes will be available by tonight in the Swayam portal. Thank you.